Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Welcome to our presentation today. So, this is the subject from ENG3002 Engineering Mathematics 2. So, our project is production of styrene from crude oil by using Smpo process, which is styrene monomer propylene oxide that we call Smpo. The method we use for first ordinary differential equation is integrating factor and variation parameter. So, our group members are me is Muhammad Arif Hamizah bin Amri, Arshad Hakimi bin Muhammad Zaidi, Muhammad Faik Hamzi bin Abdul Aziz, Hawa Adani binti Azlan, and Marsha Anna Andrew. So, we go to next slide. So, today we will discuss three main things in our presentation today, which are first is project title, second is introduction, and third is first order ordinary differential equation problem applications that we create the questions and the solution from our project ECH3123, which is material balance. Next, the title of our project that we do for ENG3002 is Production of Styrene by Styrene Monomer Propylene Oxide SMPO process. So our feedstock is styrene with gas phase at 20 degrees Celsius and the feedstock annum is 1 million ton per annum. So the introductions before we go to main agenda is we just selected two processes from the total of 47 processes in our design. Second, the chosen unit is cooler 7, which is suitable for using Newton's law of cooling to generate the differential equation before solving the equation using integrating factor and variation parameter. And technically, the cooler will act to cool the styrene, which is our main products after undergoing methylphenyl carbonyl MPC dehydration from initial temperature 146.78 degrees Celsius to final temperature which is 20 degrees Celsius with constant pressure in the unit process. And lastly, the second is we use MPC dehydration for our second problem, which was used in order to get styrene by eliminating the water from the components. Next, we go to the assumptions. There are a few assumptions that we made to make the equation valid. We have four here. First is the gas acts as ideal gas behavior, which is PV equals to nRT. Second, no heat transfer occur in any processes. Third, the scaling up of the feedstock of 1 million ton per annum, which our basis we use 100 kmol per hour in feed. And lastly, the general energy balance equations will be delta H equals to Q since no change in change of potential energy delta EP, change of kinetic energy delta EK, and work shaft. So we go to the first problem of first order ordinary differential equation ODE applications. Let's go.
Assalamualaikum warahmatullahi wabarakatuh. My name is Hawa Adani binti Azlan and my metric number is 214130. So I will continue with problem number 1. Figure 1 shows the stream 61 with initial temperature 146.78 degrees Celsius with the pressure 760 mm mercury flows into the cooler 7 with 20 degrees Celsius and constant pressure. Table 1 shows the data of the compositions of each substance. For your information, cooling process is a non-reactive process, so there is no change on mole and mass. Moving on, the problem here is write a complete differential equation by using Newton's law of cooling. Furthermore, use integrating factor and variation parameters methods in order to satisfy the process at any t time by making assumptions about the temperature depending on t time. Hence, find the temperature of the process at 180 minutes.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faik Hamzi bin Abdul Aziz and I will present solution 1. Here we go. Using the Newton's law of cooling formula, which is dT temperature over dt time equals to negative k in bracket t minus t naught. From the process, we know that the initial temperature is 146.78 degrees Celsius. So we can substitute the value into the formula. which is dt over dt equals to negative k in bracket t minus 146.78. By using the experiment method to get the general equation by integrating both sides, we got ln in bracket t minus 146.78 equals to negative kt plus c. So, t minus 146.78 equals to exponential power of negative kt plus c. Next, using the exponential formula when a equals to e to the power of c, hence we get the general equation t minus 146.78 equals to a e to the power of negative kt. In order to get the coefficient of Newton's law of cooling, K, the assumption that we can make here is the system will lower the temperature at temperature equals to 100 degrees Celsius after 2 hours, and the second assumption we can make here is the system will lower the temperature at 50 degrees Celsius after 4 hours. To find A, we must substitute both temperature and time respectively into the general equation when temperature equals to 100 degrees and time equals to 2 hours. So after we substitute, we got A equals to negative 46.78 over e to the power of negative 2k, which is the equation 1. When T equals to 50 degrees Celsius and T equals to 4 hours, we got A equals to negative 96.78 over e to the power of negative 4k, which is we can assume that is equation 2. Substitute both equations to get k. After we substitute the equation 1 and equation 2, we got k equal to negative 0.363. After we got k, we can substitute into the general equation, which is dt over dt is equals to dt over dt minus 0.363t equals to negative 53.28114. After we dy dx equals to negative fxy equals to rs. By using integrating factor to get the general equation of t, we got e to the power of negative 0.363t. Use the formula of integrating factor to get the equation of t. By using the if, when we substitute the if, we got t equals to 14.678 plus ce power of 0.363u. And then, if by using variation parameter to get the general equation of t, the first one, we must change the homogeneous linear equation to, the first one, we must change the non-homogeneous linear equation to homogeneous equation, which is dt over dt minus 0.363t equals to 0. Then, bring the t term into right hand side and integrate both sides by using the separable form method. So that we got t equals to e to the power of 0.363t. Next, we introduce the THS to start the relation parameters calculation method, and then we got Tx equal to e to the power of 0.363t multiplied by Vx. Next, we use the product rule to get the dt over dt. And then, we got dt over dt equals to e to the power of 0.363t multiplied by v prime plus v multiplied by 0.363e power of 0.363t. And then, we substitute the dt over dt and ts into the original equation. And then we got dv over dt equals to negative 53.28114 over e power of 0.363t. Next, by using the separable method to get the equation of v, we got v equals to 14.678 over e power of 0.363t plus c. And then we substitute the vx and thx into the equation tx equals to thx multiplied by vx. So we got Tx equal to 14.678 plus Ce equal of 0.3633. To get the particular solution, we must assume the value of T and T, which is the value of time and the temperature and time. When temperature 100 and time equals to 2 hours. So we got C equal to 41.28. So the particular solution is Tx equal to 14.678 plus 41.28 E of 0.363T. Based on the equation, time equal to 180 minutes is equivalent to time 3 hours. So we find the temperature and we got Tx equal to 137.33 degrees Celsius.
Hi, I'm Marsha Andrew with matrix number 215540, and let's proceed with problem 2. The inlet mixture of benzoic acid Ba, methylphenylcarbinol MPC, and ethylbenzyl hydroperoxide EBHP consists of 0.005 kmol per hour, 1.359 kmol per hour, and 0.44 kmol per hour respectively. Only 100 meter cubic per hour can be allowed to fill the reactor. As suggested by figure 2, consider that the reactor was collecting 70 meter cubic per hour of the MPC, EBHP, and Ba mixture. Then, at a rate of 50 meter cubic per hour, the gas mixture leaves the reactor. Table 2 shows the data given as a reference for the calculations. Using integrating factor and variation parameters, method to get the differential equation: A. Determine the amount of EBHP accumulated in the tank at any time t, and B. How much of the EBHP is accumulated in the tank after 4 hours.
Assalamualaikum warahmatullahi wabarakatuh. My name is Arshad Hakimi bin Muhammad Zaidi, and my matrix number is 14978. And now I will continue on the assumption and the solution. The numbers of assumption are made for this reactor include those that follow. First, the reactor functions without any failures. The reaction has completely reacted. Number 3, the rate of ethylbenzene hydroperoxide production is uniform and continuous throughout the whole process. Number 4, the reactor accumulates 70 meter cubic per mole of the mixture of methylphenylcarbinol, ethylbenzene hydroperoxide, and benzoic acid. And now we'll continue for the solution 2. Let Y denote the amount of ethylbenzene hydroperoxide accumulated in the reactor of any t time using the Balance law to produce the differential equation in this problem, which is given by rate of change of yt dy over dt equal to rate at which yt enter the reactor minus rate at which yt leave the reactor. The input rate is volumetric flow rate equal to 100 meter cubic per hour, amount of ethylbenzene hydroperoxide entering the reactor equal to 1.359 kmol per hour of ethylbenzene hydroperoxide. The output rate is volumetric flow rate equal to 50 meter cubic per hour, amount of ethylbenzene hydroperoxide entering the reactor equal to 50 meter cubic per hour times yt mol over 70 meter cubic equal to 0.71 yt mol per hour of ethylbenzene hydroperoxide. Therefore, the initial equation of problem for the solution in this reactor will be dy over dt equal to 100 minus 0.71 yt. The first assumption is the reactor has accumulated 1 kmol per hour after 0 hours. Y0 equal to 1. By using the integrating factor, arrange the equation to the general form into non-homogeneous linear first order dy over dx plus fxy equal to rs. Then we will insert the number, and we will get dy over dt equal to 100 minus 0.71 yt. Then we will solve the equation that we will get 0.7 1t equal to f. Then integrative factor will get exponential 0.71t. Then using the formula of integrating factor to get equation of y, we get y equal to 140.85 plus c exponential negative 0.71 t. By using the variation parameter to get the general equation of y, dy over dt plus 0.71 yt equal to 100. Once change the non-homogeneous linear equation to homogeneous equation, dy over dt plus 0.71 yt equal to 0. The second step is bring the yt term into the right hand side and integrate both sides by using separable form method, and we will get yt equal to 0. Yt exponential equal to exponential 0.71 t. Step number 3 is introduce yht to start the variation parameter calculation method, and we will get yt equal to exponential negative 0.01 times vs. Then we use the step number 4 is use the product rule to get dy over dt. Then we get dy over dt equal to exponential 0.71 t v the first derivative plus v times negative 0.71 exponential negative 0.71 t. Step 5 is dy over dt and yt into the original equation. Then we'll get dv over dt equal to 100 over negative 100 over exponential negative 0.71 t. Step number 6 is we use separable method to get equation of v, and we will get v equal to 140.85 times exponential 0.71 t plus c. Step number 7 is substitute the vs and yhs into the equation ys equal to yhs multiple vs. Then we will get ys equal to 140.85 plus c exponential negative 0.71 t. And step number 8 is to get the particular solution, we must assume the value ys and t, which is x equal to 0 and y equal to 1. And we will get c equal to negative 139.85. So the particular solution is ys equal to 148.85 minus 139.85 exponential negative 0.71 t. From B, we know that t equal to 4 hours. Hence, we'll get ys equal to 132.68 ethyl benzene hydroperoxide accumulated. And this is our reference. I think that's all from me. Thank you.
So, if you guys have any questions, do let us know about that. So, thank you for listening, and I will see you guys in next video. Thank you.